Hello guys and welcome back. So now we're going to start looking at pops and doing particle simulation in Houdini. And we talked about in the first week about the context in Houdini. So we have the OBJ or geometry context, we have the image for compositing, we have the out for rendering, we have the mat for material, shop also for material, and we also have inside of these guys a secondary or a second context. And when it comes to dynamics or anything related to simulation, we're going to do all that under the DOPS context, and this is what this is where the simulation happens. Now the data, the OBJ is called SOPs, the context, and the way it works, we initialize everything we need at the SOP level. So let's say we have a geometry to emit particle from, we created in SOPs, scatter points on it, and then use those points to emit particle. And this process of sending data between SOPs and DOPS can be a little bit confusing in the beginning, but it's actually very, very simple. Think of it as you have a different department or a different place where the processing of that data is going to happen. So you need to ship it in, you need to send it to this place. They process it for you, and then they give you back a product. This is what the DOP is. It's a factory that you don't have access to. You have to ship in the data, and once it gets into the factory, you can decide how it's going to be processed and working, and then you're going to extract or ship back the product, the outcome. So we're going to prepare data in the SOP, send it to DOPS, and then from DOPS we're going to send back the data that is ready. So for example, if it's a particle, we're going to extract points with information. If it's a particle sim, we're going to send static geometry, and it's going to give us back animation information that we can apply. If it's a smoke sim, we're going to give it the initial emission, density emission, or the source of the smoke, and it gives us back the smoke field again out of DOPS. So this is how it works. Let's take a look at this. We're going to create a geometry node. Let's create a grid, and I'm going to scatter some points in SOPs, and now I want to pass this data to DOPS. I'm going to create a POP network, and this is a DOP network. Actually, let's create a DOP network, and this is what we're going to be diving inside and tweaking. So I'm going to connect this first input here, and if we dive inside, you see it's different now. We're under the DOP context, and the display of data is different as well. So let me hide this for now. I'm going to delete this node, I don't need it. And this is where we create the solver. So I'm going to create a pop solver. Okay, and the data is structured differently in DOPS. It's the way it is structured is very different than in SOPs. The SOPs is top down. The solver or the DOPS is left to right and top down also. So it has two axes. And what we need first, always on the left side in this gray node here, and is the data initializer. It's not the data import, it's the initializer. So this is the pop solver, for example. We can create a smoke solver, we can create a pyro solver, we can create an finite FM solver. It's called cloth. We can create a cloth solver as well, which is the FOM, and all these guys, they have a first input that we can connect to. We can create a fluid, particle fluid solver. We can and you can see here, this is where we connect the initialization. And what we need to do for this is we need to create a pop object. Okay, this is not the emitter. This is the data holder. And this is how DOPS work. You have a core or an engine. It takes an input to prepare all the data, and then on the right side you stream in what you want to import into this. Okay, so we're going to create a particle pop source. This is our second node to import the particle or emit the particle, but these guys, they don't create the data. Okay, this is what creates the data. This is like the initializer, and this is what injects the data into it, and this is the guy responsible for doing all the behaviors. So here I'm gonna say in the emission type, I'm going to set it to all points to use all the inputs that are coming, and then in the geometry source I'm going to say use first input. You can see that it shows the points there. Now we have this. What we can do after the data gets processed, we can apply a gravity to it. Okay, so let's hit play, and you can see we have points falling through. Cool, so let's move this object up a bit, and let's dive back in. Let's hit play. Cool, so we have particle falling through, and I want to add a ground for collision. And this object is a DOP object, so it gets created here. We don't initialize it outside. We're going to create a ground plane, and the way we combine this, the way we set it up, is using a merge node. We're going to connect the first input. It has to be the first input to be the ground plane. This is the second input, and this is our third input. And now hit play. We should see collision happening. You can see the particles are bouncing back and forth, but there is no variation or anything, so they're all on top of each other. Okay, in the emission source here, we have a few options. We can set the life expectancy, how long these guys live. We can give them a variation threshold. Let's set to 1 second. 1 second. This is equal to 24 frames, and you can see they're stopping there. Okay. We can also tell it to inherit attributes from the mesh, from the input, and this is by default. So any attribute that we create at the SOP level, let's say I want to create a random color, it's gonna get inherited here. You see the color there. We can also use the given incoming velocity if we added any velocity to the points, or we can add to that data. So I want to add some velocity, 1, maybe 2 here and 1 here. So it's 1x, 2 on the y, and 1 on the z, with some variation, and this is just to add randomization to the vector. And you can see now I'm getting some force. Let's hit this to -1. Okay, cool. So let's and these we don't have. We're not going to change any of that. So let's make this live for 3 seconds, and let's add some noise to this. Let's apply what we call a force. So this is going to be a pop force node. I'm going to connect it in between this chain, and so we can chain forces or things that we want to apply to the particles at this level. So I'm going to add a pop force. I'm going to give it an amplitude of 5. Let's hit play. See, we're getting some noise now. Let's increase the swirl size, and this defines the size of the noise. You can see it there. We can make it super thin. It's very, very fine. Yeah. We can layer multiple of these. So I can copy this guy and add another one. Let's say this is set to 3, amplitude is 10. Let's copy it one more time. I'm gonna set it to 0.2, and the swirl size is 0.5. And these are a noise, just the same controller, the noise controller that we have when we create any noise pattern in Houdini. So it's just simple controls. And yeah, we can explore with these options to create some cool stuff. Now, what I want to do, I want to add a drag to this. So I'm going to add a pop drag to slow the particles down. I'm going to set the wind resistant to 0.05. This is very, very sensitive, So even a small value makes a huge difference. Let's set this to 1. And now we have our particles system. Okay, now if we go back up, we middle click on this node, we see that we have a lot of extra data added. We have all these guys, and the DOP by default, DOPS tries to give us a preview of what we have inside the context, but it doesn't necessarily mean that we have the good data that we need. Okay, we can have a lot of other things that we that are working to create the sim, but we're not interested in all of that. We just want the points back. And let me briefly talk about this node. So here it shows everything under with the star. It's showing everything inside the DOP context, and the data name, we'll talk about that later. For now, we don't have to worry. Actually, you know what? Let me explain it. So the way it works is the DOP networks creates this initializer, which is the data initializer, and then it attaches inputs or incoming or values to it. So you will see the data in the spreadsheet very, very different from SOPs, and the way it categorizes it is by the object type. So you see here we have a ground plane, we have a pop object, and if I play through, let's play a couple of frames, we should see data. So if I go under the pop object, this is what the initializer, you can see that all the data is attached to this. Everything gets attached to this. It's like a container or a placeholder. And the thing that we're interested in is called geometry. And all these is data type: forces, collider, real in-group, geometry, physical parameter. All these are data types. And at the upper level, the DOP network is displaying everything, means the pop object, the ground plane, anything. Basically all these guys, as well as importing all the data. Okay, what we're interested in is actually the geometry. That's the only thing we care about from the pop network or from the DOP network running a particle sim. And to extract that data back into SOPs, we're going to use a DOP import node. Okay, and this needs the object network, so I'm going to drag that, the object mask or the object name, so I'm going to say this is the object, not this guy, this is not the data creator, this is the type. You can see it here. Okay, I'm gonna paste that, and then what I want to do is I want to fetch geometry from DOP network. This is what I want the type to be set to. Now, to be 100% sure, I always enforce the type to be geometry, just in case there is something else that comes along. I type this to be 100% sure, and now we're only importing the points back. And you see here, if I look, there is a ground plane or anything else that we may add to the sim, like colliders, but I just want the points, and this is how you get them back. Now, there is multiple attributes that are getting added, and I don't want all of those. I am going to use an attribute delete, and I'm going to delete everything. So star for everything. Star here, and then I'm going to use this syntax to not delete the velocity, not delete the point, which it doesn't by default, and don't delete the ID if it made it. Yeah, so these are the attributes that I need, and then I don't want to delete the color because that's something I also want. And now we have cleaned up all this. Now we have a point group. I'm also going to delete that. I'm going to use a group delete node. I'm going to type in a star there. And this is my particle sim. And it's clean, ready to cache, no extra data or anything like that. Okay, so the DOP network doesn't have much by itself. There is a reset sim. By default, see this blue thing going on. It means it's caching it to memory. So if we hit play, it will cache it. And then I can play through without recaching it. This is the start frame if you need to change the offset or the sequence starts at 1001. And then the cache here, this is how much memory you tell this blue thing that it can consume. Right now the default is set to 5. It may not be enough, so we can increase it to 20 gigabytes just in case we need more. And then you can tell it also to allow caching to disk in case it fills up this much memory. It can turn and start caching, but I wouldn't recommend doing this. You only get the feedback, the interactive feedback when it's caching to memory. Okay, so how much do we have here? 32,000. A cool thing that we can check is called the, where is it? Performance monitor. Let's move this here. Okay, right now it's off. Let me reset this. You see the cache is cleared. Let me put this to be always on top. I'm gonna hit record. I'm gonna hit play. And this is a great tool in Houdini to investigate where the time is being spent and basically what's slowing the sim down. You can see the SOP. This guy is actually taking. Oh, this is the result of everything. Sorry. So the slowest part is the solver, which you can see here, 1.612, and then the other, I'm not sure, maybe that's the viewport display. And this is, you see it used color now, that's the slowest part, which we know about. So let me increase the point count 100 times, and let's hit play again. So I'm going to turn off the GPU because that also adds to the time it takes. I'm only interested in the sim. Let's pause this, and you can see that again the solver is the slowest part, but overall this is 3.7 million points now, and this is a huge sim. Okay, and it's working really fast in my opinion. So let's just change the display to pixels, and let's change this to black, and let's take a look at that as best as we could. So there is a lot of data here. Cool. And we also have the velocity, which if we render this, we'll get some nice motion blur. So I'm going to stop this. This is how you check scenes or debug things. If you have, once you have a lot of operation, you may be able to quickly narrow it down to what's causing the slowness if you see things like that. Okay, let's see what else. I think, yeah, so the next thing I want to do is I'm gonna change, come on, this should go away now. Let's open the performance monitor again. Okay, it's fine. So I'm gonna do something here inside the points. I'm gonna, after the scatter, I'm gonna add a transform, and I'm going to rotate, animate this. So let's see, this axis, and I'm gonna move it back to 0. I'll explain why. And let me change the background and add the grid back. So those are my points, and I want to rotate them like that. I'm going to use a sine function, and this will again give me back a value between -1 and 1. That's multiplied by 60, and it's not too fast, so I'm going to multiply the frame by 7, and so multiplied by 10. Let's go even more, 15. I want a fast rotating object. Cool. And I'm gonna change the, no, I'm not gonna change the scatter. I'm gonna leave the point count to be the same. And I'm also going to add a movement up and down. So I'm going to use the sine function again with the $f, and let's multiply this maybe by 4, multiply it by 10, and here I'm going to add +1 to this. And the reason for that is because the sine function gives me back a value that goes between -1 and 1. If we add 1 to it, we shift its range between 0 and 2. So this way it's not going to go back below 0. And you can see it's going up and down now, as well as rotating. So let's increase the distance it travels. Okay. Let's see. So multiply by 60. Okay, and let's add +1. I need the parentheses here. Okay, cool. And let's increase the frame range to 400. And I think this is too high, so let's set it to 30. Okay, cool. That's my object, and I'm also going to increase this to 90. And all I wanted to create is some animation, that's all. I'm going to create a trail node. I want to compute the velocity with this, because we saw that we can inherit attributes. So let's compute the velocity. And if we view that using this node here, display point trail, we should see the velocity vector. Okay, let's go inside our awesome DOP network and let's hit play. And let's hide this. You can see we have an object rotating. But what I wanted to show is, see that stepping, that specific emission there. The only way to fix that previously, or the classic way, is to increase the min and max step steps. And what this does is, it, instead of computing one time every frame, it does multiple emission or computation between the frames. So I can say the min is 4, the max is 5, and so it will do 4 times that between each frame, and this will make the sim 4 times slower. It's as simple as that. And see that it's not fixing the gap. We still need to increase this quite a bit. So let's set this to 10 by 10. This to 1. We don't need to change that. It's better. There is still gaps, definitely, but the sim is 10 times slower. So what side effects presented is something very, very cool. If we go here under the birth tab, there's this jitter birth time. It's set to positive right now, and the interpolation source is set to none. I'm gonna say I'm gonna set it to negative and try it. This, I don't have a final answer or a clear answer to this. I always try different combination. So let's try a positive and backward. So it does some interpolation, and instead of using the match topology, I want to tell it to use the point velocity, because we know that's correct. I want to use the velocity vector. See, now it's still not perfect, but it's a little bit better. So let's try forward. Cool. So now it's much, much better, the emission. Okay, let's try backward. And these are just different interpolation, and I think, yeah, forward. Let's try this last time. The match topology, it tries to compute its own velocity or its own vector that sometimes, I'm not sure why, but it results in something better than the velocity from SOPs, which is the case here. And this is the perfect motion that you can get from a fast-moving emission like this. It has zero stepping, and it's not doing anything extra. Again, I still have to try various combinations of this, but again, here, for example, with the match topology, it's not generating the correct result. So there's always I provide the vector from SOPs, and I try various combination until I get the perfect example. Now this emission, if you guys remember, this first emission was caused by the solver not knowing how to motion blur these points in the beginning because they are just getting emitted, and I was trying to fix the emission, the jittering basically, and it resulted in creating a velocity like that. So we may have to tweak that and improve it. Now let's turn this off. And we're also adding, inheriting the velocity from here and adding to it. So let's set this, let's just leave the initial velocity. Okay, let's add more noise. Let's set this to 10. Set this to 4, maybe 20. Cool. Okay, and let's add something called color, pop color. And what I want to do is I'm gonna change this guy, allow us to change the color value. I'm gonna set it to ramp, and by default it's equal to the normalized edge. And I want the color to start blue. I like blue. And I'm gonna set it to brighter blue towards the end. Okay, let's see how that looks. As it gets older, it gets brighter. Okay, let's do one more thing. Let's add to this guy. It's very cool motion. Let's add some noise to this. So I'm going to create a point VOP. I'm going to dive inside. I'm going to create a noise pattern. Let's use a curl noise this time. I'm going to use the point position, and I want to add this to the velocity. So let's take velocity, add this guy, and export the velocity back again. And let's change one frame. And let's set this to 10. And make sure we're viewing it. And let's increase the frequency. Lower the amplitude. Cool. And that should get reflected into the sim as well. So let's increase the point count to 10,000. Turn off this thing, the preview, and let's take a look at the result here. Let's hit play. Now we have our first particle sim. Cool. Let's change the background to dark. Let's turn off this, make sure it's set to pixels. Yep. And let's preview 100 frames flipbook to look at it in real time. Cool. We have a perfect emission, we have noise, and we learned how to use to inject velocity and how to import data from DOPS and clean it up. So this now can go into caching, and with the when we save it to disk, so I'm going to say $hip under sim. Okay, I'm going to call this particle sim. sim.v1 for example. I'm going to leave this as it is. I'm going to set it to 100 frames, and I'm going to increase the point count more. So let's say 100. Let's see how much it is now. Okay, let's say 100,000. And now I don't want, when I'm going to cache it either to disk local on the background, we have to turn this caching off, otherwise it's going to occupy the memory. So I'm turning that off, reset the memory, reset the sim, and then we can hit the save to background and then open scheduler. And this is a Houdini tool to basically track the progress of background tasks, and you can see the emission, the progress. Now it's going, and we can continue working or even close Houdini. If we close Houdini, we lose this UI, but it's still going in the background. But we can open scenes and things like that. And now we can read the file back in using a simple file node. And that's our data. And it's still caching, of course. And we have 2.8 million. You can see already that it's going really fast. Let's take a look at the file size. So it's 1.92 gigabytes already, and it's getting 100 megabytes here. So yeah, it can get big quickly. Okay, let's do something super quick. I like to, whenever I do test renders, I like to create separate geonodes. So I'm going to call this render particles. I'm going to paste the file and create the p-scale attribute, because that gets used to determine the size. I'm going to set it to 1 or 0.1 here, and then we can use the multiplier, which lives at the upper level of the node. So here we can go under render geometry, we can change the point scale to 0.01. And with the motion blur, there's two types. There is either an object transforming, moving through space, where the render can compute the transformation matrix and the motion blur at render time, and or we have a particle sim where the point count is changing, so Mantra cannot determine the velocity, and that's when we need to provide our own velocity vector and tell Mantra that it needs to use that. And this is done using the geometry velocity blur, and that's what we need to take that guy. So let's create a Mantra node and hit render. I'm going to leave everything as the default. Actually, I need to turn on the allow motion blur. I'm going to set this to 12 and 12. And let's leave this at 1. Let's leave this at 1 and hit render to see how this looks like. With motion blur, of course. Yeah, so the point size is quite big. But I think you guys got the idea. Cool. Thank you so much for watching, and see you in the next video. Bye bye.